introduction. Very happy to be back, and also for the kind invitation to let me speak about this work. So I should begin by apologizing for starting late, but I will try to make up for it by finishing early. So so the topic, again, this is work done with Suvajit Majumder and Evgeny Sobko, whom you should probably know to greater or lesser extents. So this is, of course, like I said, a case study in quantum integrability, but this is they are the real experts. So if they were to talk about this work, they would be speaking about it from a very different point of view. I would like to talk about the same work, but from the first part of the title, which is neural networks as Ansätze. And essentially the idea will be that if you have a set of constraints and you're searching for functions that obey those constraints, then it's can be a good idea to try to model that function by a neural network. Okay. So I really like the slide, so I can't imagine not starting with it. So here's this quote by Marvin Minsky at IBM in I believe the 60s, that artificial intelligence is essentially the science of making machines do things which would require intelligence if done by humans. And just as an example, I was looking for the attribution of this quote, and I couldn't find it, and I couldn't remember the exact quote as well. So I fed it into ChatGPT, whatever vague thing I remembered, and I asked it that, can you tell me the correct quote and attribution? And it said that it gave me basically the correct quote. And the idea, and it's quite a complicated sentence, right? There are various levels of syntax and context, and somehow the correct meaning it's able to identify. Whereas if somebody were to do something, then something else would happen. It's a fairly convoluted sentence. So, but coming more to physics, it's at least arguably I would like to say that it's essentially a new methodology for thinking about physical systems. And in the following sense, that conventionally, if you were to ask somebody to solve a solution to a set of equations or whatever, I mean, analytically, there's a certain set of steps that one could do, but also computationally, there's a certain set of steps one could do. Say, you could try to simulate things using, say, Monte Carlo, or you could use some differential equation solver. But there's always this idea that you tell the computer what to do. And but AI is different in that sense. So rather than telling the computer what to do, that here's a systematic set of steps that you need to take to solve something, you tell the AI what the solution is, and then you let the AI kind of infer how to arrive at it. So for example, so this is very famous, but let me tell you just in a few words about this, because it's kind of related to what I'm going to say. Computing metrics on Calabi-Yau spaces is actually quite a difficult problem, and it's one of the big obstacles to doing string phenomenology, because any geometric data that you wish to extract from your Calabi-Yau compactification is usually prohibitive to get. So in that sense, it's an important problem both in algebraic geometry and also in string theory. But to solve this, at least one way to do it is to use what is called an energy functional that was proposed by I think Matthew Heydrich and Nassar. And you can think of, you can tell essentially the neural network that a Calabi-Yau metric is the function that minimizes this energy functional. And then lo and behold, the neural network gives you the Calabi-Yau metric. Okay, it's a numerical form, but that's usually the best one can do anyway. And a small refinement of this is to provide constraints on the solution. Okay, so let me tell you a little bit about why it's a good idea to to do this using neural networks. And this is really the point of the title, that neural networks is Ansätze, because you could imagine doing the same thing, right? And any undetermined function, you could say that, okay, I will expand it in the, say, basis of plane waves or Legendre polynomials or whatever, and then I will try to fix coefficients depending on, so that the constraint is obeyed. So
constraints are like mostly equations, or you can handle inequalities as well?
Yeah, usually equations. Yeah, equations. You could probably do inequalities, but let me come to that. Yeah, it's equations. Yeah. Okay. So neural networks. So here's some inspiration from biology. So basically, a neuron is something which takes in some inputs, and at least as far as we can tell, what it seems to do is process those inputs into a certain output. And then that output is fed into further and further neurons, and then that's how we perceive the world around us, hear things, etc. So and especially in the 1950s, when when these things were discovered, there was a lot of optimism that humans are almost perfect thinking machines. Probably misguided, but there was this idea that humans are perfect logical reasoning machines, and the way to build an intelligent machine is to mimic how a human brain works. So this was basically an artificial neuron which was constructed by Rosenblatt in Cornell, I think in the 50s. So what it does is that it takes some inputs, takes a weighted sum of those inputs, acts on it with a shift, and then applies a nonlinear function on it. Okay, so these are basically tunable parameters, the weights and the biases. Okay, and f is usually nonlinear, and it's also non-polynomial. You can make it linear, but it doesn't buy you much. But linear models are nonetheless useful toy models. Okay, so so the simplest example is really a step function. So what will happen here is that when this weighted sum wx plus b, it crosses a particular threshold, then from 0 the neuron instantly fires to 1. So this is a very intuitive picture of how what a neuron is, right? It receives an input, and when the input crosses the threshold, it fires. This is not always the best thing to do in practice, but there are ways of smoothing it out, for example, using tanh. So yeah, so just a little bit of notation. So imagine that instead of one neuron, you have k neurons, and you can index them with k, and you can write down this equation, right? It's essentially a linear sum with a nonlinearity, acting pointwise. So for this should be zk, sorry. So for z1, a1 is f of z1, so f of z2, and so on and so forth. So it's pointwise. And also, like hindsight is 2020, let's call this the 0th layer. Let's index it with 0. Yeah. And then you can write this particular thing as just the L is equal to 1 instance of this more general equation, right? And now that you've done that, then to get higher, quote unquote, higher layers, all you have to do is iterate this transformation, right? So, and this is basically the simplest neural network. This is what is called the multi-layer perceptron. And of course, you might ask that other kinds of topologies possible? Yes, they are. There are many different ways of arranging this. You might ask, can you have different activation functions for different layers? Yes, you can. Within a layer, yes, you can, but you wouldn't call it the same layer. Things like that. So most generalizations that you might imagine from this framework can be done.
How do we iterate the BLKs?
No, we don't. At every layer, there's a new BLK added.
So the objective would be to determine W's and D's.
Yes. So I will just come to that in a moment. Yeah. So, but you can see that there's this very pretty hierarchical structure. So you have this. Sorry.
Layer means different scale of this.
Yes. So this is one layer, for example. This is another layer. This is another layer. Yeah. Okay. So basically, you have this input. It is acted on by this layer of neurons and produces some A1s. You take that as an input, act on it with this layer of neurons, produce another set, and then so on and so forth. Okay? And the output function is whatever's collected over here. And basically this can be changed for a given fixed input by tuning those W's and B's. So as Anindo asked, the idea behind finding a desired function is essentially to find that particular configuration of W's and B's that gives you that desired function. Okay, and in this talk I will not comment at all about how best to find this thing, but if you wish, the answer is essentially in practice first order optimization. So all that is fine. I mean, it's a nice picture from biology. It was very popular at some point. At another point, there was actually a paper, oddly enough, by Minsky, who killed off this entire thing, and there's a whole history there, and then it just came back with a vengeance in the future. So somewhat like physics, there was this really popular set of ideas in the 1960s and 50s, which were the only thing being limiting them from actually doing any of the things we are doing today is just computational power. I mean, that's a slightly trite way of putting it, because of course there have been new insights, but the really key thing that they were missing is computational power. They simply obviously didn't have the kind of GPUs and all that we have today. Okay.
So what is the time frame that you're looking at? So these neural networks that you said, Rosenblatt introduced them in 1960s?
1950s.
1950s?
Yes.
And then Minsky killed them when?
Roughly around the 60s. So 51, 52 they were introduced. 60s, I think it was Minsky. They wrote this paper which basically constructed very simple things that kind of a neural network couldn't solve. Okay, and then basically, and the resolution is actually very simple, and actually many people have wondered that why, like, it's just staring at you in the face, how to resolve that problem. But apparently Rosenblatt also knew the resolution, but he died at an untimely this thing. So basically, everyone just shelved it. Like, okay, so.
And then it came back. I mean, so it became a major research topic.
So this cycle kind of repeats itself. So in 1988, Jeffrey Hinton and Rumelhart proposed how to train these networks using first order optimization. Then they showed that it's a viable thing to do, actually, because remember, there are billions of parameters. Then again, it kind of died because even using that, it was very hard to train networks. Then around 1995, Jan LeCun invented the convolutional network, which won the image recognition challenge. Again, there was a lot of interest, but to actually initialize and train these networks reliably, you need a certain set of best practices which didn't really come online until as late as, I would say, 2010 or 2014. So things like how to initialize the network. Earlier, it was more like an art than a science. I mean, and certainly nowhere that, like today, somebody like me can just write 3-4 lines of code and train a network. That was in no way possible. So, okay. So let me just tell you a little bit about why these networks are so appealing. And a very classic problem is what is called supervised learning. Supervised because you're literally telling the neural network what the right answer is in some cases. So you start with some set of input-output pairs, and basically you tune the weights and biases of the network so that for the input pairs, for each input, approximately the correct output is obtained. Okay, there is some reason for this approximation. I can talk about it privately if you wish. But the claim is that that these neural networks are actually universal approximators. So by that, what we mean is that this kind of a data can always be modeled by some neural network. Okay, and again, I'll be giving you an intuitive reason for this, but really, and I will not make any claims about how easy or hard it is to actually do this. And there are essentially two reasons driving this universal approximation. One is the width of the network, which is basically the number of neurons in each layer, and the other is the depth of the network, which is the number of layers. Okay, And essentially what I will show you is that these infinite width neural networks are universal approximators, but
Sorry.
yes.
Does it depend on the configuration or the total number of parameters?
Well, it depends on this configuration that you need the infinite width for it to be a universal approximator. Okay. Usually, of course, this is none of these are actually practical limits, but you kind of have it in the back of your mind that even for modest size. So, for example, we considered 50 neurons. So, like following Ed Witten's joke, 1 over 50 is very small. Okay.
Width was this way and depth was this way.
Yes, yes. It's a little confusing, but yeah. Okay. So here's the idea. Supposing you're given this target function of input-output values, huh? So here, some interspersed values and on. So what you can do is that you can try to approximate that function by this kind of a histogram, right? And the more the number of target values are, the better the histogram you can make. Yes. So this is the basic idea. And now what I'll show you is that you can design a neural network using that step function, which can build this histogram for you. And that is, of course, not that hard. You take a difference of two step functions. So you get a bin. You multiply that by the height you are looking for. So you get that particular histogram bin. Yeah.
One more is you can approximate only in that range, right?
Yes.
Outside it's almost impossible.
Yes, that's actually, thanks for that question. Most of those, most of these, that's actually an important question in machine learning, interpolation versus extrapolation. And usually these networks are so parameter rich that you don't really expect it to work outside of the data that they're actually trained on. There are, however, some curiosities. There's something called grokking, for example. So here the neural network was given, it was asked to learn the multiplication table of the group S5. Okay, and it was given part of the multiplication table. So as you can imagine, it learned that very well, and it was just learning junk in other places. Now, what happened was that they overtrained the network to some ridiculous length, and then somehow, almost miraculously, it did learn the correct multiplication table of S5, which is quite remarkable. Yeah, but again, this is just a phenomenon. There's no understanding of this at this point. Okay. So, like, you can see that a single layer of neurons basically yields a universal approximator. Yes, you take your inputs. Each of these things will give you one bin. You add up all the bins together, and then that gives you this output neuron. Okay. So the question is that why do we need depth? And depth is really needed for learning, not memorizing. Because this, you might say that, well, this is fine, but you just basically as you pointed out, you're essentially memorizing data, right? You're just like memorizing a function that spits out correct answers without even caring about what might happen even in the intervening points, right? So. And you can play like interesting games. You can basically generate a set of random data, just random numbers, and you can ask a degree 300 polynomial to fit it. It will fit, but when you generate new random numbers, it will of course give you junk. So so basically depth is actually what is arguably where the learning lies. So so imagine that you have some kind of hierarchical structures in your data. So for example, images, like the way we process vision, at least that's what I understand, is that we have a set of primitive neurons that can basically detect edges and kind of differences between light and shadow and things like that. And then you have the more like the neurons that are deeper in the visual cortex, which synthesize those primitive inputs into the actual complex shapes, patterns, and all that we see. So and that was the idea behind having this multi-layer thing. But indeed, if you see that, if there's some kind of a hierarchical structure like a sawtooth, then imagine that you have one function like this, another function with 2 peaks, then this one with 4, and then this one with 16. Then you would say, following that argument, that okay, if I need one neuron to memorize this, then I need 2 to memorize this, then I need 4 to memorize this. But that's really not doing anything, it's just memorizing. But if you allow depth, then what you can do is you can use function of a function. So one sawtooth is this, but if I compose this, then I will get this. If I compose that again, I will get this. So then this really corresponds to a single input, but just 4 neurons. So you can see it from the point of view of, say, parameter efficiency, this is a very much better thing. And also arguably, if you're training, especially in real life data where there is really no ground truth, so there's no deep reason why my face looks like this and not like something else. So there's no ground truth as such. So you have to be very careful that you're effectively not learning on random noise, which is always a concern when you have billions of parameters and millions of data. Yeah, the number of parameters you have is just much more. So when you see things like this, basically what the network is doing is that it's really trying to isolate features that are essential for it to classify data. Okay, so from that point of view, also you get a bit more confidence that things are working as they should be. And
instead of this, if we use a slightly more sophisticated things of training on primes, will it be able to predict primes, or will it be able to recognize it? How to identify primes?
If I knew that, then I would probably be relaxing on some island in the Bahamas.
So it's not that?
No. Well, so far all attempts have failed. But it is true that there are certain more sophisticated questions about primes you can ask, like how do you bound the difference between primes and things like that. So that, although neural networks haven't been actively deployed on it, but variants of machine learning, say like genetic algorithms, that they have, and they have been able to narrow down those kinds of bounds. Yeah.
Yes. Given data, like all the planets, like typography.
Yeah.
Can you find the
I guess you could actually think of the first analysis of Brahe as being a machine learning problem so basically he did linear fitting with engineered data, right? And he was fitting t square against r cubed, and then he found a straight line or a log plot or what. So I mean, in that sense, that is also this kind of a machine learning problem. It's just that there.
So with that data, it could have found that.
It could have found, yeah.
Like 1 by r.
Not 1 by r. Well, also 1 by r if you stay far away enough from r is equal to 0. Because there are questions of like numerical stability and things like that in training this. It's not as roseate as. And also the thing is that if you do more conventional machine learning, the kind which Brahe actually did, which is like you take the input data and you arrange it into features that like that this is the log of t and this is the log of r. Then once you fit the data, then your answer is much more interpretable. Here, the answer is very hard to interpret in human terms. So, yeah, okay. So today, what I'll do is try to use neural networks to tackle a problem in quantum integrability, which is essentially to solve the Yang Baxter equation. And the idea will be to use the same neural network on different classes of solutions and show that we can recover all known classes. And more than that, I will try to show you at least some thought experiments which are aimed at getting new solutions, that how starting from a given class of solutions can you try to expand into a more general class. Yeah. So here, the cases where I'm talking about, it's all explicitly known. So it is a little bit like, okay, post hoc ergo propter hoc, but it's at least like it's a very clean kind of a system where because we know the answer, we can kind of like play in that little playground. Okay, so yeah, so let me tell you a little bit about loss functions. So this is actually goes back to what you were asking, that can it find inequalities also. So basically the way we are currently training the network is is using loss functions. And the original idea is that basically you just evaluate how good or bad the predictor is. So, for example, you could give it the mean square error, which is what Brahe would have given, and you can tune the networks so that you minimize in W. Right? Intuitively, at least, basically what this is saying is that if LW is small, then on the coarse grain thing, the predictions are good. Right? We have to divide out by the size of data, of course.
So, why is it just a function of W? There was this intercept as well.
Yeah. So W and B, but yeah. So it's kind of like because no one wants to carry around all those things. So what many people do is they define x0, which is equal to 1. So then WX plus B is W0, and you think of B as W0. So WX plus B is just WX. Okay. So yeah, but also what? Yeah.
It's one. So there's this thing called a constraint, which is inequality.
Yes.
And then there's a loss function, which is sort of an inequality.
Yes.
I had a constraint which was an inequality, like something is possible.
Yes.
And I would ask it to minimize that quantity, basically given zero. I could just, that constraint I could just put as a loss function.
Yeah, you could solve for something being equal to 0 like this, but yeah, something being greater than 0, it might be harder. Well, what you could do effectively, like, you could kind of, if you're looking for those things, you could train so that essentially at the end of the neural network, you have very low dimensional representation of data, and you're solving for something being equal to 0, and then you could try to play around in configuration space and see where it becomes positive. But it's very, I really don't have anything to say about that. Yeah. So basically, this is the idea that this should be ideally 0, but really not so. Again, just ask me about this more, but it has to do with fitting noisy data. So if you're fitting noisy data, you don't really want this thing to become 0 because you are learning noise. So, but basically you want to minimize this within reason, and that's the target. So conceptually, it's not very different from ordinary least squares. Yeah. One difference in practice, again, is that the loss function is no longer convex. It's kind of easy to see. I can show you later. Although formally it looks like the same convex function of least squares, if you think of it as a function of W's, it is not convex, and it's very easy to see. But I just want to, I can show it to you later. Yeah. So of course, now you could ask that, okay, since I'm trying to minimize this loss function and it's minimized at 0, so when is this loss function 0? Okay. So this loss function is 0 when y of xn is equal to y of yn. So basically what you could say is that minimizing L is basically searching for functions such that y of xn is equal to yn, and you could think of these as constraints on the function. Yes. So, and loss functions are constraints in the target function, and they are 0 when the constraints are satisfied. Okay. It's just a small generalization. But this is actually a very powerful generalization. This has to do with Siamese networks, which were invented to solve a very practical problem, that of recognizing signatures on bank checks. So, I don't know how many of you have done this, but you have to sign a check and give it to the bank, and the bank would match your signature on the check against the signature on records. And this was done in the 80s actually, so it's quite quite a sophisticated thing. So of course the question is that how do you train this thing? You cannot give it a million examples of everyone's signature, and then by the time you finish training, half those people have left, and so many more people have joined. So this was like, again, Geoffrey Hinton. Somehow there are these couple of names who always appear with this thing. So he had this ingenious idea, and which was that you think about how humans learn. Yes, and this is an example due to Fefeli, that if you have a toddler who's kind of learning animals, and you say that this is a cat and this is a dog, then maybe you have to show it 2 or 3 more times, but after that they know, right? There's no no notion of having to see a million cats. And then the next time it classifies, it identifies things as cats and dogs depending on what things are most similar to. And of course, the better the training, and also one nice thing is that it fails gracefully. So if you show it a fox, it will say that it's a dog, weird looking dog, but a dog. Okay.
But there are two methods, and
I can show you the. I'll show you this thing in a moment. Yeah. So again, so this is the idea that this toddler, what it is learning is this equivalence relation that 1 and 3 are same, 2 and 4 are same, but 1 and 2 are no longer the same. Okay. So essentially, the idea which Hinton came up with many collaborators. What he came up with is to quantify the idea of similarity. Okay, and the idea was that from your input data, which is the space of images, you learn a map into RD. So the neural network, what it is doing is that it is learning a map from every input point to a corresponding point in RD. But the map satisfies a property. Okay, and it says that if x1 and x2 are similar, then they should be mapped close together. This is just the Euclidean geometric distance. And if x1 and x2 are dissimilar, so for example dog and cat, they should be mapped far apart. So in this sense, you see, this idea of similarity is kind of encoded into the geometry of this representation space. And then when you are trying this thing on new data, you just take the same neural network, take your input, see where this thing gets mapped and what it is closest to. Yeah, that's your inference step. So, okay. So if you wanted to prepare this data, then you would prepare data in the form of pairs x1, x2, and the output is 1 if the data is similar and 0 if the data is not similar. And you see again, so the loss function is not mean square, but it is this thing which is not super different. It's a bit hard to understand, but the intuition is the same, right? This is 0 when for y is equal to 1. When this thing is the only thing that contributes, this thing will go away for y is equal to 1. Then d has to be 0 for this thing to be 0. But when y is equal to 0, this thing drops away, this contributes. That means max of 1 minus d and 0 has to be 0, which means d has to be greater than 1. Yes. So basically, what this loss function is doing is trying to learn a map such that this idea of similarity is encoded. Okay. And the way, of course, since you asked about the network, the way this thing is encoded is basically you have data x1, x2, and then you have your network. So it's the same network, and then it gets mapped into this RD, and where you compute distances. Okay, and this is why it has this unfortunate name of a Siamese neural network, because it is two twin networks joined at the hip. Okay, so here's the summary of all things neural networks. So if one of the things neural networks are great for, especially when thought of post hoc, is doing an exhaustive scan across functions. Especially so, for example, if you're doing, say, computer vision or natural languages, you have no idea of what basis to write your prediction function in, right? I mean, how do you even start? And in fact, a lot of work pre-neural networks went into constructing precisely, such kind of functions, which filters for computer vision to do this thing. So, but when you have less of an idea, neural networks can be very useful. But also, more than just making predictions, they can learn abstract properties, like the idea of similarity. So rather than saying that, okay, this is what a cat is and this is what a dog is, it's trying to learn what are the features that make two dogs similar but a cat and a dog different. Yeah. So it's really learning something much more sophisticated. It's like at least your first course in biology is that. So, okay. So, and again, like, let me remind you that it can learn very abstract properties, but I didn't tell you how to tune these weights in practice. Okay. You can imagine that if you do, if you have n weights which take 10 values, just for sake of argument, then your search space is 10 to the n, and if n is 1 billion, then random search is not going to fly. Yes. So, so tuning these things in practice is actually, sorry. tuning these things in practice, again, this is just a throwaway remark, is actually a very important analytical problem also. This is again where a lot of people are using intuition from physics. Like you think of a ball rolling down a hill, down to its this thing. So what is the best way? So gradient descent is obviously one thing, but adaptive steps, incorporating momentum, things like that, and also there are subtleties to do with the loss function. But yeah, tuning, how to tune this in practice is actually a very important problem which physicists are contributing to. Okay, so quantum integrability, and again, like I said, I have no idea about quantum integrability, but this is just to kind of set the application and just in the stage, as it were. So if you imagine a spin chain, then you consider a spin chain, periodic spin chain with L sites, and I'll shortly give you an example. And the Hilbert space at each site is say some complex vector space of some dimension d, and we'll look at d is equal to 2 in this talk. And imagine that the Hamiltonian only allows nearest neighbor interactions. Then there's actually a set of spin chains which admit infinite conserved charges, and they have all been exhaustively classified. Like if you remove all possible, gauge redundancies, choice of bases, this, that, and the other, then there are 14 independent families, which the classification was completed in 2019. But here's the construction. So you have some d square times d square R matrix that's basically valued in Vi in the tensor product of two nearest neighbors, and the charges are basically encoded in derivatives of u. So for example, this at u is equal to 0 is the two particle Hamiltonian, and of course this obeys this complicated cubic equation, and so there are d square so there are d square times d square functions. So it's a huge dimensional search space, and there's this one constraint that it obeys. And if you wish, it also obeys this constraint, or it obeys constraints like locality. I'll just come to that. Yeah. So the question is that which we wanted to address is that how do we construct integrable systems from scratch? Right. So here we know the answer, but there's at least an expectation that when you make the dimensionality of the site Hilbert space larger, you should get more and more and more quantum integrable systems. So how do we construct these from scratch? So so this kind of smells a bit like bootstrap, but it is and it isn't. Okay, so let's just take it with a pinch of salt. So we start off with some underlying assumptions, and then we look for functions that obey those assumptions. Okay, so you assume that the R matrix is holomorphic, it's local, which means that R of 0 is some fixed quantity. The target Hamiltonian also you assume is known, or at least something is known about it. And this is not that big a deal, we can relax it, and I will do this in a moment. And the R matrix must obey the Yang Baxter equation. Yes, so these are the only constraints. Yes, and of course then there are natural questions that you might want to ask. What if only constraints on the Hamiltonian are given, right? Because at least here we know that there are not 14 integrable systems, but 14 families of integrable systems, and I'll show you something.
What is the significance of the Yang Baxter equation?
Oh, that is the yeah, that's the defining thing. Yeah. So okay, so you might want to ask that, okay, I don't want to specify actual numbers for the Hamiltonian, but I do want to specify some equalities, algebraic equalities. Say 2 entries are equal to each other, or the sum of some entries is 0. I'll show you examples. Okay, and also, like, given integrable systems, can you find other integrable systems in the vicinity of that one? Okay, and of course, like I said, neural networks span a large function space, and you will see that the solutions are complicated. But not only do they span a large function space, it's easy to write quote-unquote the Ansätze. All you have to do is give the architecture of the neural network and all the activations, and that's your Ansätze. Yes, it's easy, quote-unquote, easy to write the Ansätze. It's quote-unquote easy to supply the constraints. You just define the appropriate loss function. So here's the setup. So you have some set of functions. They are holomorphic. At r is equal to 0, they obey this and they collapse to these fixed numbers. At the first derivative at 0 is the Hamiltonian, and then of course we have this Yang Baxter equation. And the task is to learn what these functions are. Part of this we will. In some cases we know. I mean, say for example, Heisenberg's spin chain. Yeah, yeah, yeah. So you could say that, okay, yeah. Let's assume that at least for the moment you know what the Hamiltonian is. Okay. Okay. So a part of this we will kind of build into the architecture of the neural network, so that by construction, so especially this holomorphicity, we will design the network in a way so that by construction it learns a holomorphic function. Okay, and the rest we will implement using loss functions. Okay. And of course, here's the idea that now you have all of these scalar functions, and there are a priori 16 entries in the R matrix. So 2 square times 2 square 16. So of course, these are complex in general, so really 32 neural networks. So basically what is being trained is not a single neural network, but an ensemble of 32 neural networks. So yeah, it's quite sophisticated. Yeah, and the functions that are entering basically obey are constrained not like on themselves, but roughly against each other. So like, you know, some particular complicated cubic in those functions is 0.
So what is this third level 1 and 50?
Oh, so this is the number of neurons. So this is the first neuron in that layer, and this is the 50th neuron in that layer. Yeah. So yeah. So this is basically, if you wish, the Ansätze. Yes. About holomorphicity, in principle, there is no well, we can do the training in the complex plane. The only thing is that typically you don't get holomorphic functions, you get meromorphic functions, which are kind of a beast to handle, because as you're tuning weights and biases, it might be that, you know, suddenly some pole appears in the domain of your training. So it's kind of not the easiest thing to work with. So what we did was that we trained on the real line, on a real interval, but we designed the network so that there's a natural analytic continuation. So we chose a holomorphic activation function. So if you have this kind of function, this is just holomorphic. Yes. But if weights and biases are real and this input is real, then this thing is real. So if you want to take a complex function which is complex even on the real line, then in general you have to take this combination. But this is holomorphic. I mean, it's just by construction. Okay. So overall, the structure kind of is very reminiscent of the Siamese network. So you have this real line from which you're learning these maps. These maps have certain constraints. So if you have this as the set of all possible maps, then there's a set R for which R of 0 is equal to P. There's a set where R prime gives you H. So you're looking at the intersection of that. And then within that intersection, you're looking for solutions that solve the Yang Baxter equation. Okay, and this kind of intuition is actually very important for the analysis. Okay, another way of putting this is that you think of exploring function space, and so this box is basically all the R matrices that can be represented by the network. The orange submanifold, if you wish, is the set of functions that obey the Yang Baxter equation. The blue submanifold is like, you know, other constraints like locality, form of Hamiltonian, etc. So basically the idea is to find this intersection and move on this intersection. Yeah. So, and that is the intuition with which we will do the rest of the analysis. Okay, so finally, like this is some concrete results. Okay, some concrete results. So typically in D equal to 2, solutions are of this form, and this slide is a little superfluous because I'll show you better things. Yeah. So consider this Hamiltonian. Yeah, this is what is called the XYZ model. So nearest neighbor interactions. And at each site, the Hamiltonian is basically the sum of Pauli matrices at every pairwise this thing. Okay, And of course, now this is the most general Hamiltonian, but then there are these symmetric limits, Jx is Jy, and Jx, Jy, Jz are all the same. So the XXZ model or the Heisenberg or the XXX model. Okay, and these systems are all integrable. So yeah, so let me show you what they look like. The XYZ models are actually parameterized by real numbers eta and m, and two parameters because we're fixing Jx plus Jy is equal to 2. Okay, so that constraint is baked in here. And also, so you can see that, okay, these are some Jacobi elliptic functions, and the solutions of the R matrix are also quite sophisticated. Yeah, you can see there's this the elliptic in eta and m, and they are also elliptic in u. Yes, and so for example here, this is elliptic sign of u. So it's quite a complicated function. Now for the XXX model, actually m is 0, because then if m is 0, then Jx is equal to Jy. Yes, so that's the XXX model, and then you will see that all of these elliptic functions essentially go away, and all you're left with is exponentials. So much simpler. Okay, so here's a graph, because why not? So yes.
Those are the known analytic results.
Yes.
And so what is exactly going to be our output?
The output will be just those known analytic results right now. And I'll show you something more sophisticated in a moment.
So at a particular point in u, you get a number?
No, I mean at a range of u, you can you will get a function from each neural from the neural networks, and those functions will match.
The neural network is going to be a function.
Yes, yes, it'll give you a function. So basically, it's something which has weights and biases, but at every value of u, you can evaluate it, right? So it's still a function of u. So yeah, so you evaluate.
Interpolating function?
Yeah.
You're comparing with these.
Exactly. And usually it's better because, the Yang Baxter equation, there's always this freedom of dividing out by some overall complex function and all. So what we actually look at are ratios to do the match. And then you can see that, these are two curves, but they practically lie on top of each other. Okay. Yes, but that is really where you know everything, and it's just a sanity check. Like, if that doesn't work, then basically nothing else will. So let me show you the ideas that we had for kind of exploring the landscape. So this thing over here is tests and results. Originally was called experiments and results, but then I thought of writing experiments and my courage failed me. So it's called tests and results. So the first experiment, this is why I said that the XYZ is much simpler than XXZ. XXZ is much simpler than XYZ, is how do you get XYZ starting from XXZ? Which means that you start from the m is equal to 0 limit of the model and essentially navigate away from that. Okay, that's why that idea of having intersecting functional spaces and on which you're moving, that's why it is so important. So basically what you do is you train this network with some, again, this is just a sanity proof of concept check, but you train this network with some value of eta, and m is equal to 0 for some time. Okay, you train it for a bit, say 10 units. 50 units. You fine tune, then you fine tune a bit more, or essentially, like you could think of training to 3 starting points: eta pi by 3, pi by 4, pi by 6, and m is 0. Okay. Now, having done that, you have 3 XXZ models, which are your starting points. Okay. Now you randomly sample some non-zero values of m, and you train with those target values. Okay, so then we find that we actually do converge to those correct loss functions. So this is actually what happens, that if you train to XYZ, you see the Yang Baxter equation is very well satisfied, and then suddenly you turn on those extra m not equal to 0 targets, and then of course everything goes haywire, but then the system starts to kind of go back to being solutions again. Yes. So, but that was again assuming that you kind of know that there's something like XYZ, and you're basically trying to so basically, like supposing you have a conjecture that this particular class of integrable model should be embedded in a bigger class, can you find the bigger class? Yeah, so that would be, but also imagine that there is this class of integrable models, and actually, so these are all complex numbers, by the way, now, okay? So this would be arXiv if they were real or whatever, yeah? So here there are actually two classes. This thing is integrable if either A1 is A2, if these two are equal, or there is this equality between the A's and B's, okay? And the aim is to discover these two classes, okay? And again, I mean, the idea is that, you know, kind of use this as a playground, because here we really know the answers, so we don't have to like go through the pain that we are currently going through, which is like, how do you really make sure that these things actually are integrable and all, okay? Okay, so you train to some integrable Hamiltonian, so you train to some subspace here, and then what you do is that you try to move away from it. Okay, so you give it a little kick, so that so again the intuition is that you're still on most of those submanifolds in function space, but maybe you move slightly away. Yeah? And then you train again, and just requiring that the Yang Baxter equation is satisfied and locality is satisfied, but you don't give any constraints on what the target Hamiltonian is. And you just let the network, you know, just find what it finds. Okay. And then you collect all the Hamiltonians that were found, and then you find that, and this is again just to convince you that, you know, we actually did this. But when you want to visualize the learned Hamiltonians, you do see that they either obey A1 is equal to A2 to this very fine degree, or they obey A1 plus A2 is B1 plus B2 also to a very fine degree. And again, I mean, having these clusters is one thing, but getting them out in high, well, even 6 dimensions is high. So in a high dimensional space is kind of a sophisticated question. So again, like in showing you this, I'm kind of assuming that I already know that that these are the loci, but finding this is again, you know, something we're doing right now. So, but at least in this case where we know the answers, again, it's much easier to show quite clearly. Okay.
When you actually trained,
yes,
you used only one class, is it, or?
No, yeah, we gave it, I think, one class, yeah, or just one condition, one number.
Okay.
So actually,
and
just
it was clever enough to actually.
Yeah, and then we said, so once we found it saturated, then we just kicked it away and let it evolve to whatever. We're just requiring that the Yang Baxter and locality are satisfied. So, and we kept doing this thing of like saturating to something, then kicking, then saturating, then kicking, and things like that. And so essentially, even though we say started in class 1, at some point it went over and started exploring class 2 as well on its own. Yes. 2 subclasses of, yes.
Using similar ideas, would it be able to classify Lie groups?
Yes, I hope so, but I'm not, yeah. Yeah, so okay, so here's the summary of the talk. So as I said, neural networks are universal approximators, and it's very intuitive to use neural networks. So maybe you don't care about quantum integrability, but you might care about solving constraints without having a good idea of what basis to expand your function in, what kind of an ansatz to use. Neural network can be very useful there. Okay, so if you don't have a good ansatz and you know the constraint, at least intuitively, then you can set up this kind of an architecture. This is quite sophisticated. There are these things called physics-informed networks and all, but at their heart, they're basically doing this, that the differential equation in that case is the loss function. Okay, so basically, we use this to solve the Yang Baxter equation in a very restricted family where we know all the solutions exhaustively, and we could actually recover them. But because we know all the solutions, we could try to play games and like try to invent strategies for exploring the space of integrable theories. Now, so currently what is in progress is like finding these kind of new solutions in 3D etc. And of course, then there are more sophisticated follow-up ideas. So just as a teaser, so we are like working on this, so this is a bit premature, but if you imagine that the local Hilbert space is three-dimensional, then the R matrix is 9 cross 9, which means 81 independent functions. So these are some Hamiltonians visualized in some weird way. It's not a terribly meaningful plot. The only meaning it carries is that we have found these solutions. Okay, and that's all. So and characterizing them and finding out exactly what models they correspond to is in progress. So yeah, so that's all I have to say. No, it's yeah. It's yeah. So this Deleuze and all, they had this method of using the boost operator, but even then they comment that in 3D, just the number of unknown functions using their method just goes up. Yeah. Yeah. Hopefully, let's see. I mean, obviously, like, you know, such a simple-minded thing will not work, but there could be ways that, you know, that maybe this can give us some intuition for arriving at what kind of a class to look for analytically or something like that. Yeah.
So in the XZ and XYZ.
Yes.
So you trained it using the XXZ.
Yes.
And then you found the XYZ as a...
Yes.
By kicking it away from...
By kicking it away, so that was a slightly different thing. We were actually giving it some value of XYZ to converge to. But we weren't, we were using the XXZ as a kind of a warm start for XYZ. So in a sense, like quantifying this idea that somehow XYZ is close to XXZ in function space. Yeah, so at least, like, you know, when you take M to 0 smoothly, at some point XYZ just becomes XXZ. Yeah, so that would be like, you know, supposing you have some reason to expect that, you know, I have this model, but I also do expect that, you know, like if I turn on some more entries in the Hamiltonian in some controlled way, then that should still be integrable. So then one can do that and try to check. Yeah, that was the basic intuition. Yeah, but in general, like I'm not going to lie and make grandiose claims. It is subtle because the loss function is 10 to the minus 8. Yes, but the Yang Baxter equation being equal to 10 to the minus 8 is not a thing. Right, it's actually 0, right? So you have to be careful. So I'm not going to, like, you know, give some evangelical statements that, you know, everything is solved.
And what kind of computing resources do you need?
Oh, you need a GPU for sure, but it's much less intensive than, say, somebody like a proper HPC or anything like that. So basically, if you had a standalone GPU, that would be enough.
There are not local integrable chains.
Yes. Right. Yeah. Yes. I guess so. Yeah. Right. Non-local. This thing. Yeah. I guess so. Maybe I don't know. Maybe in some sense that would be. Yeah.
Here, where is the locality?
Locality just goes into saying that R of 0 is equal to the permutation operator. So yeah, if one can relax that, then it's just removing one loss function actually. Yeah, maybe one possibility could be to even in this as a proof of concept train to maybe some, say, Hamiltonian values and Yang Baxter equation and locality, and then turn off locality as a loss function and maybe even the Hamiltonian, and just let it evolve, just solving the Yang Baxter equation, and then. Okay. I see. This is for the 1 over n corrections, those pendants, or?
Like the SU2, even the planar case, it's actually non-local.
Oh, okay.
Not just IJ.
I see. So, but they are of non-difference form, yes?
Sigma I and sigma I plus.
Okay.
instead of 1.
Yeah.
Yeah, I think it comes at next order 1 by L correction.
Oh, okay. So, so the R matrix, so I specialize to the case where R of, so there are two spectral parameters, and these ones, the R matrix really turns out to be a function of U minus V. So, but there, I think they are independent functions, yes? Okay.
Still they work with R matrix.
Okay.
The whole n equals 4 planar chain,
Yeah.
that is not planar. In fact, it's like, if you take 1 by L corrections, it interacts with R.
I see. Yeah, that
Almost infinity it
becomes local. I see. Yeah.
That's supposed to be unique. That supergroup thing is unique.
Oh, okay. Yeah, it might be interesting to try to figure out. Yeah, it could be. Probably it's well posed also in this language. I'll try to take a look. Thanks.